We now discuss the solution of a problem from the section Complex Analysis. The problem is on Cauchy-Riemann Equations. This question has appeared in the CSIR National Eligibility Test held on 16th February 2022, and it is from the part C. The given question is, for any complex valued function f, let d suffix f denote the set on which the function f satisfies Cauchy-Riemann equations. Identify the functions for which df is equal to c. We are given four options. Option 1, f of z is equal to z by 1 plus mod z. Option 2, f of z is equal to cos alpha x minus sin alpha y plus I multiplied by, in brackets, sin alpha x plus cos alpha y, where z is equal to x plus iy. Option 3, f of z is equal to e power minus 1 by z to the power of 4 if z not equal to 0, and f of z is equal to 0 if z is equal to 0. Option 4, f of z is equal to x square plus I y square, where z is equal to x plus iy. And here we are given a complex valued function f, and df denotes the set on which the function f satisfies Cauchy-Riemann equations. Then we have to identify those functions from among the options 1, 2, 3, 4, for which df, d suffix f, is equal to c. That is the given question. We have f is a complex valued function defined on the complex plane C, and f of z is equal to u of x comma y, the real part of fz, plus I vxy, where vxy is the imaginary part of f of z, and d suffix f is equal to the set of all those complex numbers at which f of z satisfies the Cauchy-Riemann equations. Let us recall the Cauchy-Riemann equations for fz at a given point z0 is equal to a plus ib. The Cauchy-Riemann equations are, first, the Cartesian form is ux is equal to vy and uy is equal to minus vx. This is the Cartesian form at z0. And we have a complex form for the Cauchy-Riemann equations. Dou f by dou z bar is equal to 0. It is the complex equivalent of Cauchy-Riemann equations. And dou f by dou z bar, where z bar is the complex conjugate of z, and dou f by dou z bar is equal to 0 at z0, and ux is equal to vy and uy is equal to minus vx, which are Cartesian form at z0. Then we say Cauchy-Riemann equations are valid at that point z0. Now we take the option 4 first. F of z is equal to x square plus iy square, where z is equal to x plus iy. Here u of xy, that is the real part, is x square. The imaginary part of fz, v of xy, is y square. Agreed. Now let's see the Cauchy-Riemann equations. ux is to x, vy is to y. ux is equal to vy implies 2x is equal to y, implies x is equal to y. And uy is 0 because u is free from y, and v is free from x, therefore vx is 0. So uy is equal to minus vx is equal to 0. So the Cauchy-Riemann equations are valid only at those complex numbers z is equal to x plus iy, where y is equal to x. That means all those complex numbers that lie on the straight line y is equal to x, there only the Cauchy-Riemann equations are satisfied. Therefore, d of f is not the whole of the complex plane. So d of f is all those complex numbers at which f of z satisfies Cauchy-Riemann equations is equal to x plus I y. Y is equal to x. So x plus ix belongs to C, where x belongs to R, is not the whole of the complex plane. Therefore, df is not equal to C for the function in option 4. Agreed. We continue, and let us take the option 2. F of z is equal to cos alpha x minus sin alpha y plus I in bracket sin alpha x plus cos alpha y, where z is equal to x plus iy. And there is nothing is given on alpha, therefore we assume alpha not equal to 0. So that is the major constraint on alpha. So right. So now u of xy is cos alpha x minus sin alpha y. Yes. V of xy is sin alpha x plus cos alpha y. So ux, that is the partial derivative of u with respect to x, and the is equal to vy, partial derivative of v with respect to y. Right? That is ux is equal to the derivative of cos alpha x is minus alpha sin alpha x, and the derivative of cos alpha y with respect to y is minus alpha sin alpha y. And that will imply sin alpha y is equal to sin alpha x. That will imply alpha y is equal to alpha x plus 2n pi, where n is set of integers. Yes. This implies y is equal to x plus 2n pi by alpha. So df is the set of all x plus I y. Y is x plus 2n pi by alpha belongs to C, where x belongs to R. So at these points only the Cauchy-Riemann equations are valid. So which is not equal to C, and hence df is not the whole of C for the function in option 2. Move to the next option, option 1. That is f of z is equal to z by 1 plus mod z. And mod z is under the square root of z bar. So we have f of z is equal to z by 1 plus mod z, that is equal to z by 1 plus under the square root of z bar. Now take the derivative, partial derivative with respect to z bar. So you are differentiating partially with respect to z bar. So z works out as a constant. So z into the derivative of 1 by 1 plus under the square root of z bar, that is minus 1 by 1 plus under the square root of z bar whole square into the derivative of root of z bar, that is root z comes out, and the derivative of root z bar with respect to z bar is 1 by 2 root z bar. And dou f by dou z bar will be equal to 0 only when z is equal to 0. Only when z is equal to 0. So that means CR equations are satisfied only at one point, namely z is equal to 0, that is the origin. So d of f consists of a singleton set consisting of 0 complex number 0 alone, which is not equal to C. Therefore, d of f is not the whole of C for the function in option 1. So we have seen we go to the remaining option 3. So for option 3, d of f must be equal to C, because the remaining 3 are or false. D of f is not equal to C for option 1, 2 and 4. Therefore, one answer must be there. Therefore, for this function in the option 3, D of f is the whole of the complex plane. And let's look at this problem. And in our MSc classes, this is one of the examples what normally we do it in the class. And it is a very familiar example. And now, dou f by dou z bar is equal to 0 when z not equal to 0. When z not equal to 0, this function e power minus 1 by z power 4 is independent of z bar. Therefore, its partial derivative with respect to z bar is 0 when z not equal to 0. So that means the Cauchy-Riemann equations are satisfied for all z not equal to 0. That means on C star. So what happens at the origin? So we talk about the Cauchy-Riemann equations at the origin, and it is a very tedious one, but however I will show you. So first e power minus 1 by z to the power of 4 I will expand. For z we write x plus iy. So you will get e power minus 1 by x plus iy whole to the power of 4. Rationalize the denominator. So multiply numerator and denominator by x minus iy. The denominator becomes x square plus y square whole to the power of 4. Now x minus iy whole to the power of 4, expand it. So take the power of 4, use the binomial, and we get this one. So this will be equal to e to the power of minus 1 by x square plus y square to the power of 4, right? And the real part is x to the power of 4 minus 6x square y square plus y to the power of 4. And the imaginary part is minus 4xy into x square minus y square I. So this will be equal to e power minus the real part into e power I into that imaginary part. So e power I theta, for this cos theta plus I sin theta we will write, that is e power the real part and multiplied by cos of theta is this plus I sin theta. Great. Now we want to get what is u of xy and v of xy. We will see in the next slide. So that's what we have seen, and this is your real part. So e power minus x to the power of 4 minus 6x square y square plus y to the power of 4 by x square plus y square to the power of 4 cos of that theta plus I e power the first one into sine of that theta. Agreed. So u of xy will be the first part and v of xy is the second part. So u of xy is the with cos, and when x comma y not equal to 0 comma 0, and it is 0 when x comma y is equal to 0 comma 0. So also v of xy. With v of xy we will get sine. Agreed. Now, right, this is what we have seen. Now ux, that is del u by del x, ux at 0 comma 0 is limit h tends to 0, u of 0 plus h comma 0 minus u of 0 0 by h. U of h0. So you get into u, put x is equal to h, y is equal to 0. Then you will get minus h e power minus h power 4 by h power 8. And that is e power minus 1 by h power 4. And cos of 0 is 0. Minus u of 0 0 is 0 by h. Now put h is equal to 1 by t. Then you will get h, the h is sitting in the denominator, then you will get t by e power t to the power of 4 as t tends to infinity. And it will take infinity by infinity form, which is an indeterminate form. Use L'Hopital's rule, differentiate the numerator, that is 1, differentiate the denominator, that is e to the power of t power 4 with respect to t is 4t cube. So limit t tends to infinity 1 by 4t cube into e to the power of t to the power of 4, and that will be 0. So ux, that is ux at 0, 0 is 0. And uy at 0, 0 is limit k tends to 0, u of 0, comma 0 plus k, comma minus u of 0, comma 0 by k. And so you get into this and put y is equal to k and x is equal to 0. So k power 4 by e power k power 4 minus k power 4 by k power 8, and that will be e power minus 1 by k power 4. U of 0, 0 is 0 by k, and it is same as here, and we do the same thing and we'll get the answer 0 as above. So ux is there, and v of x comma y, and v of partial derivative with respect to x at 0 comma 0. So you leave all this, and you will write x is equal to h, y is equal to 0. So y is equal to 0 means sign will be 0. So that is why it is 0 minus 0 by h. The limit h tends to 0, it is 0. Similarly, v y at 0 comma 0 is 0. Now we see ux is equal to vy, both are 0. uy is equal to minus vx, both are 0. So thus the Cauchy-Riemann equations are satisfied at the origin. So when z not equal to 0, the Cauchy-Riemann equations are satisfied. When z is equal to 0, the Cauchy-Riemann equations are satisfied. Therefore, df is the whole of C for the function in option 3. So the answer to this question is option 3. And that is the detailed discussion of the solution of the problem on Cauchy-Riemann equations from the section complex analysis. I am sure that you have understood the solution of this problem, and I wish you all the best. Thank you.